that f of g composition identity on V is same as f of g, and f of identity on V composition at H is same as f of identity on. So I can just say that f of identity on V is same as identity on f of V, which is V cap, which is identity on V cap. So therefore I can say that this is a functor. This is called the duality functor for vector spaces. It is from vec opposite to vec. It assigns to any vector space its dual. So I would end this lecture by giving some exercises to the students. So first exercise, so few exercises for students. So one is stone functor. Stone functor. So what is this stone functor? It is from top opposite to top. The category of all topological spaces, opposite category of topological spaces to the category of Boolean algebras. So exercises show that S from top opposite to bool. Boo is actually the category of Boolean algebras and Boolean homomorphisms. Okay. Defined by, so S from top to bool that assigns to each topological space, to each topological space X, topological space X, the Boolean algebra of its Klopen subsets. So the closed and open subsets of X give rise to a Boolean algebra. So this S assigns any topological space X to the Boolean algebra of the Klopen subsets of X. And for any continuous maps, because the arrows here are continuous maps. For any continuous map from X to Y, topological space X to Y, say it is F, that is for any morphism from Y to X, F in top, because this is in top opposite, so in top it would be from Y to X. So a morphism SF. So what is SF? So SF is given by, so SF acting on any this SY, the Boolean algebra of the Klopen subsets of Y. So let a subset taken in this Z here in this Boolean algebra SY. So SF of Z is F inverse Z, the inverse image of Z. So the inverse image of Z would be in this Sx, because under a continuous map, the inverse image of any Klopen subset is a Klopen subset. So F inverse Z. Okay. So show that it's a functor. Is a functor. So it is called as the stone functor. So if I summarize the situation, so I have this. Here I have the category top opposite. Here I have the category top. Here I have the category bool. So to any topological space X in top, I have X here, but the arrows in top would be in the reverse order. So here I get this Sx, the Boolean algebra of Klopen subsets of X. Now suppose I have an arrow from X to Y in top opposite. So here in top it would be from Y to X. Okay. So what does this functor S do? It maps this to Sy, the Boolean algebra of Klopen subsets of Y, and sends Sx to Sx, the Boolean algebra of Klopen subsets of X, and this arrow F, say F, it goes to Sf, where Sf is defined in this fashion. So exercise for you to verify that this does satisfy the axioms of functor. So it is a functor. And another exercise, if C and D are two monoids, we know that any monoid can be considered as a category, or two monoids considered as categories, then functors from C to D or precisely monoid morphisms. Precisely the monoid morphisms. Monoid morphisms from C to D. Okay. Now at last we will discuss one example, again a very nice example, from a monoid considered as a category to the set category. Okay, so this is very nice example, and we will finish the lecture. So let n equal to, so let C equal to this monoid considered as a category, where the composition is just the composition of the elements of M, and identities are just the identity of this monoid. Is a monoid considered as a category. So if I take any set, so monoid considered as a category, the object is only n. There is one object in this category. Now let X be any set. let X be any set, and if I define a mapping star from M cross X to X by any M comma X goes to M star X, such that the following properties are satisfied. Such that first I have this. Suppose I have two elements M and M cap. So M dot M cap star X is same as M star M cap star X. This is for all M and M cap in M, X in X. And second, E star X, where E is the identity of this monad. E star X is X for all X in X. So if I have a function star with these two properties, then I will say that this monad M acts on the set X. We say that M acts on the set X. Now with the help of this action, I can define a functor from this monad considered as a category to the set category. So define f from M to set by in this fashion. Suppose I have an arrow from M to M, that is M, and F acting on this object and arrow gives, so F of M. So F of M is X, F of M is X, and this M goes to Fm, where this Fm is nothing but the action of this monad on this set X, where Fm of any X is M star X, the action that I defined here. Then we can easily verify that this is a functor. Then F can be easily verified as a functor. Functor from monad considered as a category to set. And conversely, if I have a functor from monad to set, then so the axioms of functor, they are straightforward, so I leave for you to verify these axioms. But what I want to say is that the converse of this is also true. Suppose I have a functor f from M to set. I can get the action of this monad on some set X with the help of this functor. Okay, so is a functor. I can define the action of monad on some set X with the help of this functor. So define how? See, define star from M cross say some set X to X by M star of X. You take it as Fmx. Okay, you can easily verify that this is an action. This is an action of monad on X. So there is a one-to-one correspondence, you can say, between the actions of monad on a set and the functors from monad considered as a category to the set category. So hope you enjoyed this lecture. So we stop this lecture here.